Think of a basic first-degree equation as a physical balance scale. To isolate the unknown, x, you follow a simple mechanical logic. Subtract the constant from one side and divide by the remaining coefficient. This system only breaks down in two specific scenarios. If the coefficient of x is 0, but the constant is not, the math collapses into an impossible contradiction. But if both are 0, the scale becomes a perfect identity, a mirror where every possible number is a valid solution. But for centuries, mathematics was halted by a much more formidable obstacle, the second degree, or quadratic, equation. Here, the unknown exists in two different states at once, both as a linear value and as a squared one. You cannot isolate x through simple subtraction or division, because the squared term and the linear term pull the equation in diverging directions. To solve for one, you inevitably complicate the other. This wasn't a mere logic puzzle.
Determining the trajectory of a projectile, or the area of a plot of land, required a reliable, universal method to navigate this conflict. Modern algebra manages this conflict using a specific engine called the discriminant. By processing the raw inputs of an equation, the alpha, beta, and gamma, this calculation predicts exactly what kind of answers are possible before we even attempt to find them. If the discriminant is positive, we know for certain that the math will branch into two distinct real solutions. If the result is exactly 0, those two paths merge into one, creating a single double root. But a negative result indicates a structural impossibility within the real number system, meaning no solution exists on our physical number line. This makes the discriminant an essential predictive tool. It provides the layout of the solution space, letting a mathematician see the end of the road before they've taken a single step. How we arrived at this tool is a story of three different historical breakthroughs. In the 11th century, the Indian scholar Sridhara tackled the problem through a geometric technique called completing the square. Sridhara multiplied the entire equation by 4 alpha. This forced the disparate terms to lock together into a uniform geometric block, allowing him to extract the unknown without being hindered by complex fractions. Centuries later, the French mathematician François Viet approached the same problem using a strategy of substitution. Viet swapped the variable x for a specific algebraic expression designed to make the linear term vanish. By forcing that middle term to cancel itself out, he simplified the equation until the solution became obvious. Finally, the English analyst Thomas Harriot worked entirely in reverse. He assumed the answers were already known and used them to reconstruct the original coefficients of the equation. 3 different centuries, 3 different continents, and 3 entirely different methodologies. Yet all 3 men converged on the exact same formula. Their work demonstrates that mathematical rules aren't just arbitrary inventions. They are consistent, inescapable conclusions dictated by logic. We still use these ancient strategies to solve advanced problems, like this 4th-degree biquadratic equation. At first glance, the x to the 4th term seems to break every rule we've discussed, but we can apply the principle of reduction. By temporarily defining a new variable, y, as x squared, we can rewrite the entire problem. The intimidating 4th-degree equation suddenly transforms into the standard quadratic structure we've already mastered. We solve for y, then plug those results back into our original definition to find the true values for x. This process of reframing a complex problem until it looks simpler is the exact strategy utilized by Sridhara and Viet. Algebra rewards this ability to see patterns and simplify complexity. It is the art of reduction, the process of stripping away the unfamiliar until only a solvable core remains.